Now we talk about, as we go into these exponential functions, the number known as e. Now e is a very special number, kind of like pi is for like some situations in geometry. E is for certain exponential functions. So I'm not going to go through every detail of this presentation, what's written here, because this is basically all written in the book. But basically, if we were to take, a situation using the compound interest formula where we have 100% interest, haha, good luck on that one, and that you deposit $1 for 1 year. So we're letting basically our R value, our T value, and our initial amount P all be 1. If we look at that and apply the compound interest formula and basically just change again the number of times we compound the interest, if I do some quarterly compounding where where M is 4, I get about 2.44. If I go for daily compounding, where again our M now is 365, I get about 2.71. If I continue doing this and keep making the value of M bigger and bigger and bigger for this little thing here where I have 1 plus 1 over M to the M power, we see that, and this is the reason why we were noticing before that when I was applying compound interest, that when all I was changing was the amount I was compounding the interest, it was leveling off because it's reaching a constant is what it's doing. And if I have this circumstance where, I have M, where basically I have R, P, and T all equaling 1, and M continues to get bigger and bigger and bigger, I approach this constant, which is 2.71828 approximately. And that's what E is defined to be. As I keep getting bigger and bigger and bigger as far as M values go, which now I'll change it to N, which is why I don't know why they use the letter M for the compound interest formula, and they use N for this. But E is actually a limit as N approaches infinity. Give me a second here. It's actually a limit of this function right here. So it's a value that we approach and we approach and we approach. So E is about 2.7182818. And basically, it's the same thing with pi. The reason why pi is irrational and some of these square root things are irrational is because, in essence, we basically are evaluating it by, trying to be closer and closer to a certain amount at that point, and we're using limit concepts to deal with it. So that's what the number E is. Now, one of the things that they will sometimes show you is that they give you a circumstance which you're never going to see out in the real world, where they mention something that's called continuous compounding. So basically, the formula that we make use for continuously compounding interest is that, the final amount A is going to equal the principal P times E to the RT power, where again, R is the interest rate written in decimal format. So for an instance of continuously compounding interest, find the value of $1,000 at 8% interest compounded continuously for 20 years. So I'm going to just make use of that formula. The final amount is going to be P times E to the RT power. So I do 1,000 times E to the 0.08 to the 20th power. And, I plug into my calculator. Now, most calculators have the ability to access E pretty easily. Most calculators do have a natural log button, LN. We'll talk more about the natural log momentarily. But, basically it's usually you have to hit the second or shift button to get to E. And so if you evaluate it using the calculator, because it gets kind of tough not to, you get about $4,953.03. So let's have you give it a try. Kind of going back to the example where we talked about compounded interest. here is our, situation we had before. Except now, as you saw, it was starting to level off, and I'm not expecting the continuously compounded interest to be much higher than what I saw for hourly. Like as you see, we already started leveling off at about 9967, 9968, somewhere in that ballpark. So I'm not expecting that big of a difference, but take this information now and now compound it continuously. So let me give you a moment to do that, and then we'll go over it. Okay, so again, all we're going to do is plug this into the formula we have for continuously compounded interest, where A is going to equal the principal, 5,000, times e to the 0.069 times 10 power, and I get $9,968.58, which if you compare it to the previous slide, all you're going to notice is that that's basically 3 cents more. What continuously compounded interest kind of does? It's kind of a again, it's a situation you're never gonna find a bank account or even a credit card charging you interest that's going to compound that continuously, because the growth is going to be continuous essentially. So like usually you have a period of time before the interest is applied, and you could whereas if you have continuously compounded interest, if I start the day with like, if it was like a debt and I had like $5,000, by the end of the day it might be $5,040, well, that's because it's continuing to grow through the day, and that, no one would want that. And certainly no bank is going to give you a bank account where you're continuously growing in value just based off of interest during the entire day. I mean, so, now they kind of go into like present value for the same circumstance, but all you're doing is essentially, rearranging your compound interest formula for continuously compounded interest. So here they show the present value of $5,000 to be paid in 10 years at 7% interest compounded continuously. All you're going to do is take $5,000, because if we set it up, and I'm looking to get $5,000 in the future, I'm looking for the present amount of that. I'm going to have 0.07 times 10. And that's all they're doing is they say, okay, well, to rearrange that, all I'm going to be doing is 5,000 over that e to the 0.7. So that's where they get it from. You don't have to memorize a new formula to do this. So, I'm going to kind of skip through that because it's going to, okay. So basically, they give you some of the intuitive meaning behind the continuous compounding. Under quarterly compounding, your money is, in a sense, earning interest throughout the quarter, but the interest is not added to your account until the end of the quarter. So basically, you have to go through the entire quarter. Your money is exactly the same, and at the very last day of the quarter, boom, it gets shot up. Continuous compounding, as I said before, it's basically you taking your interest rate, you're breaking it up into an infinite number of infinitely small parts and applying it an infinite number of times. That's why it's really not a realistic circumstance. But your money is earned with no delay. It's constantly earning money, or the interest is constantly being applied. So again, you don't see anything in the world do that. But when you talk about growth of things that are like biological, because that's another thing that exponential functions are used for, like plant growth and things like that, you are going to see that growth occur over time. It isn't like, you have a plant that started at 2 inches tall and then a week from now it's a foot tall. It isn't like it's just like, you went 6 days, 23 hours and 59 seconds, and it still stayed at, a couple inches, and then bam, it shot up 10 inches right in front of you. It doesn't work that way. It went up a little bit each time it went. So they talk about comparing interest rates, and really all to compare interest rates, percentage rate and the number of times it's compounded. They say just use $1 and do it for a year, but pick any dollar amount and any time period and apply them and see which one gives you more. I mean, that's all or less, depending on the situation. So, they make it sound like it's a really difficult thing, but it really isn't. So, for an example, which gives a better return? 16% compounded quarterly or 15.8% compounded continuously? Now, under most circumstances, if the percentages are different, it's going to favor the higher percentage, no matter how many times you compound it. But since here we're talking about basically a 0.2% difference, the number of times it's compounded might have enough of an effect on the overall application of the interest to make it noticeably more than having a higher percentage rate. So in this instance here, if I take 16% compounded quarterly, so if you take $1 for 1 year's time and apply this, we would get approximately, at the end of that year, about $1.17. If we take 15.8% compounded continuously for that same period of time, that $1 for 1 year, I would get about $1.17.1. So we're talking about 0.1% difference between the two. I mean, which really isn't that much, and with all honesty, unless you work at a gas station, you wouldn't notice it. So, so it is a little bit better, but most times, just simply changing the number of times you compound something. I mean, it's better to have like 16% interest compounded anything than say 14% interest compounded anything. So, the percentage rate is always going to be the more prevalent factor in determining the final amount, not the number of times it's compounded necessarily. Here, comparing interest rates, the actual percentage increase during 1 year is called the effective rate of interest. And you might see this brought up in other books. I know I taught Math 400, which was basically, a finite math course. We went over effective rate. It's also known as the annual percentage rate, APR, or the actual percentage yield. So, you have a nominal interest rate, which is like, when we say, okay, you're getting this percentage rate, but as soon as you say, okay, now I'm going to compound it quarterly, well, that's going to mean you're going to have a different effective rate, because essentially, when you look at when all is said and done at the end of the year, your amount did not go up by like the 14% that you were told the percentage rate was. It went up a little bit more because of the times you compounded it. So that's what we call the effective rate, or the annual percentage rate, or the annual percentage yield, or whatever you want to call it. It's different in different textbooks. So, and they go more into how, graphing the function e is not much more different than graphing the other exponential functions we talked about. It's always important to know that e to any power is positive, because, again, we're dealing with exponential functions. Any function that we're going to be looking at is going to have a value for the base to be positive. Well, e is just replacing that base. It's just a specific value for the base. It's an irrational value for the base, but that's what it is. And it kind of goes into more graphing things about that, so it's not as important here. But here's what I want you to do. Here's a situation where we use an exponential function. I want you to try to answer this question based off of the information we know about e and exponential functions now. The cost of winning a seat in the House of Representatives in recent years has been approximately 1.67 e to the 0.056x million dollars, where x is the number of years since 2012. Estimate the cost of winning a House seat in the year 2022. Now let me pause here for a moment so that you can try the problem and answer the question, and then we'll go over it. Okay, so in this circumstance here, they're telling us that X is the number of years since 2012. So basically, X is going to be whatever my year is now, which is 2022 minus 2012. So we're talking about X being 10. So the cost that we're looking for here is going to be 1.67 e to the 0.056 times 10. And this is in millions of dollars. So if I work that out, give me a second here. I get about 2.924. So that means that the cost of winning a House seat in 2022 is approximately $2,924,000. So that's the answer to this question here. If you have any further questions, please feel free to contact me.